Good morning and welcome. My name is Radu. I'm a professor in Stony Brook. This is joint work and actually primarily the work of my students, Chen, and Xiao Liang has also contributed. Bogdan Carbunar is one of our collaborators. He's in Florida International University. So in today's talk, this is an SoK paper, and it refers to this thing called plausible deniability. And the problem I'm facing with this is that it's just not easy to describe the whole SoK, a whole SoK paper in 12 minutes. So my goal today I would be happy if we all go home understanding a little more about plausible deniability and some of the challenges that are faced here. I'm not going to use too many Greek letters here, and I'm not going to talk about proofs or security models or other things. Just not enough time to do that. I'm just going to try to focus on, getting you the essentials to get a little bit of info on this field. So let's see what's going on here. So what's the problem? Why do we need this new thing? What is this new thing? Well, the problem is this, right? You have encryption and you use encryption for data privacy. And the problem that happens right now is that increasingly governments realize that encryption is very, very powerful as a tool in protecting yourself. And so then there's increasing anti-encryption laws. In addition to oppressive governments, you see this in Western governments, like the UK government, the Australian government. There's hundreds and hundreds of examples where courts have compelled disclosure and laws are enacted that are supposed to protect the children, but at the end of the day weaken significantly the infrastructure, the backbone of privacy techniques and tools such as encryption. And so now the problem is, is there something you can do about this? And plausible deniability aims to provide an answer to that. And the general idea here would be that when people have coercive power over you, so let's imagine you have a device here, and on this device you have some data. So here's your data. And this data is encrypted with some key, right? And so what happens is somebody can coerce you to provide this key. So here's your oppressive government or your bad guy. And now you're being asked for this key. And so you have to provide this key K, right? And so the general idea behind plausible deniability would be to build a mechanism that allows you to still respond to such rubber hose attacks gracefully and, yes, disclose key K and so on, and potentially fighting it a little bit and so on. But at the end of the day, also allow yourself to additionally hide additional information. I'm talking about plausible deniability for storage. Plausible deniability has a bigger story that has to do with plausibly denying actions or interactions or other things. I'm talking about storage right now. So you're going to have the ability to also have some hidden data here, and you're going to be able to somehow store this hidden data on the same device, and while still being able to plausibly deny that you actually have this hidden data. And so now, and usually what you're going to do is you're going to encrypt this hidden data with another key, with a different key that you're not going to reveal to the bad guy. And so basically what you're trying to achieve here is the ability to still get privacy guarantees, potentially through encryption somehow, while at the same time being able to be responsive to rubber hose / coercive attacks. That's the general idea of plausible deniability in the context of storage. And the problem we're facing with, and there's a bunch of challenges here that we're gonna have to deal with. So let's look a little bit at the adversary. So what can the adversary do? If you want to build systems like this, you have to think of the adversary, obviously. So obviously the adversary knows the design of the system, all right? So we're not doing secure by obscurity. The adversary can access the device, and this is a key point, once or multiple times, and we'll see where that becomes important. The adversary can coerce disclosure of secrets. We already discussed that. The adversary can question the very reason for using the plausible deniable capable system. And this is a problem. We'll see how, we're not going to see this, but this is one of the things we discuss in this. Okay? How can we provide a reason for using the actual PD system? Why are you using the system that also provides plausible deniability? You're a suspect. You can't convince me that you're not having hidden data. You're using the system as plausible deniability. Oh, well, my system also allows me to encrypt data. Okay, great, but is that enough? And can you do better than that? And then But the adversary is assumed, reasonably so, to be computationally bounded, obviously, to be rational. This is an important one, meaning that, okay, if the adversary cannot prove the existence of unrevealed data, or if you is sufficiently convinced the adversary that there's plausible reasons for using this device and for you're responding to a rubber hose attack, there's no further coercion. So this rationality will play out differently in different scenarios. And then very often the adversary is assumed not to have access to runtime system state, because otherwise you're fighting against God, and you can't fight against God. So the adversary can be there on your shoulder 24/7, looking at everything that you do. It's going to be very difficult to build any system where you can still hide information and use that information meaningfully while the adversary sits on your shoulder, even though in certain cases that's possible. So these are some of the important things that the adversary that you have to consider when you're looking at adversary in this context. And so now let's see what people came up with. So I'm going to show you a thing that's called Truecrypt. I suspect most of you guys may be familiar with Truecrypt, or many of you are. If not, here it is. A 10-second summary on Truecrypt. So Truecrypt is one of these systems. It's very cool. It disappeared now, basically. There's a bunch of forks of it. The original team disappeared under very suspicious circumstances. I mean, it disappeared, but they stopped working on it. And the idea with Truecrypt is this, right? You have some device. This is your disk. And on this disk, you have a bunch of volumes. These are your public volumes. Public volume. Another public volume. And when you're being coerced by the bad guy, you can provide, and these things are encrypted, obviously, you can provide some encryption keys that you use for these public volumes. So there's some encryption here, and there's some more encryption here with the other key, right? And that's all fine and dandy. So you can respond to a coercive attack. And then, however, crucially, what Truecrypt does is it says, hey, look at all this free space here. Why don't we store something in this free space? Why don't we hide a volume here? This is going to be something like an encryption with some hidden and randomized. So I'm going to have a random number there in my data. So this is going to be the randomized volume that I'm storing here. And I'm not going to provide this key to the bad guy. So this is what Truecrypt does. The obvious problem with this, many problems, but one of the obvious problems is, wait a second, if the bad guy can see my device multiple times, we discussed that this is one of the things the adversary can do, it may see that this region here is supposed to be free has changed, despite the fact that there's no changes in the public volumes at all. And so that alone will reveal the fact that there's something hidden here. So Truecrypt does not survive, Truecrypt survived a thing called a single snapshot adversary, but does not survive a multi-snapshot adversary, right? And so there's been a lot of work in people building systems for multi-snapshot adversaries. And so now this brings us to some of the challenges that have to do with plausible deniability, right? So here's a couple of the challenges. Security efficiency trade-offs exist all over the place. In anything you build in security, obviously, but in this case specifically, one of the main trade-offs has to do with single snapshot versus multi-snapshot. Single snapshot is usually fast, but your security is not very good. Again, why is this important? Well, because you cross the border 3 times, the adversary can see your device 3 times, or you leave your device in the hotel room. It is encrypted, so the adversary cannot see the data, but it could start breaking your plausible deniability mechanisms. If you'd want to do multi-snapshot, you get better security, but you're much slower. You either rely on write-only ORAM, as you'll see in the paper, or you have to make all kinds of assumptions or relax security requirements. And that's not as good. Then you have a dependency on system layers. Most of the existing work out there builds plausible deniability in some layer out there. Oh, this is my file system, it's plausible deniable. Great. But then the assumptions are that the underlying layers behave properly in a way that supports this. And that's very rarely the case. The typical example is an SSD. If you have you build a software block device on top of it, or you build a file system on top of some block device on top of an SSD. And then you assume that the SSD, for example, honors an erase. You say, hey, delete this block. Why? Because later you want to guarantee that the snapshot does not include that block in that form or whatever. And you're assuming the SSD will do that for you. But unfortunately, as you know, because of wear leveling and a million other things, the SSD does not do that for you. And in fact, it may keep that data lying around. So if you open up the SSD and start reading EEPROM chips, you can start seeing all your transcripts and everything else you wrote before, effectively breaking anything you've done at this upper layer. So you have to be aware of this multi-system layer story and solve it. You can't just say, I'm going to give you a plausible and deniable file system when the underlying block device will keep traces of everything you've ever written. So you can't do that, and we have to solve that. And we show directions and ideas on how to solve that, and we're providing a general story for that in the paper. And then there's a lack of a unified security framework. What that means is everybody and their grandmother comes up with some new ways of defining how secure their stuff is, which is usually what happens in our community. And the problem is it's very hard to compare things both from a security point of view and also from an efficiency point of view, because mind you, when you pay a lot for security, in security for a performance trade-off, you're going to get a very efficient system, but it's going to have shit security, and vice versa. So here's some of the contributions of the SoK paper. And again, we don't have time to dive deep, but we're happy to, please do read the paper. And if you're thinking of building plausibility using an existing system into something that you build in a broader system, or you want to build your own plausible system, you have some ideas, don't be shy, please reach out. So some of the contributions have to do with, we're addressing dependency on system layers. So in this SoK paper, we're not only summarizing what happens out there, but we're also saying, can you address this dependency? And we're providing this trace-oriented security, which basically says you have to look at the full transcript throughout all the layers. Anything that ever moves on this device has to be part of the trace. And based on that trace, you define what trace-oriented security, you define a security game that defines what security means here. It's a meaningful security game that actually you can use to prove things and disprove things about existing system. But we show that it comes at the price, the equivalence to WRAM, very slow. We address the lack of unified security framework. So we build a unified security framework that has flexibility to capture a lot of stuff, existing stuff and new stuff, and allows you to compare things. And we provide you additional insights, how to achieve what is called invisibility, how to hide data, how to hide access patterns to hidden data, and also what other future directions some people are working on or you may want to work on. This is basically it. I'm at the end of my 12 minutes. If you want to reach out, please reach out to r@zxr.io or any of us. You also have the full version of the paper, which is larger online. Thank you very much, and hope you got something out of this.